Chapter 10, Rolling, Torque, and Angular Momentum. Samples. Sample 1, a uniform rod of mass m 2 kg is hung from the ceiling at two ends, as shown in the figure. Find the instantaneous tension when the left rope is cut. This one is cut, the tension is on the right rope, right? Let's see how can we find this one. Okay. Let's draw the diagram of this rod. Two forces acting on it. One is gravitational force acting on its center of mass. One is the tension rope acting on this end, the right end. We did know this right end is O. Then, according to the Newton's law, we can write two equations. One is transmission. mg minus t equal to ma. Second is rotation around this point, axis O. Okay, we see mg half L equal to I alpha. This I is the inertia of this rod around this O. Alpha is its angular acceleration. These two equations, you have a T, A, alpha, 3 unknowns. So we need one more equation to solve that. This relationship. We look at this point, it has A center of mass. And if from the rotation point of view, this A equal to R alpha. This R is half L. So we get A equal to half L alpha. Now these three equations, we can find the solution. Very simple. This is a junior high school math. Okay. And this I, we can check it at the table, or you can use the parallel theorem. Okay. This is the inertia at center of mass. This one. Okay. This is this whole mass, center mass around this, the inertia half L. So this is mL squared over 3, okay? Then we get the answer. T is for the C. At the beginning, you see the rod is at rest, velocity is 0, but it has acceleration. A is not true because we have this A, okay? Sample. One end of a massless core is tied to a spring of spring constant K, 20 Newton per meter, fixed on the ground vertically. The other end of the rope cord is connected over a pulley of radius R 0.30 meter and inertia I around its axis 0.5 kilogram meter square, about its axis to an object of mass m 20 kilogram on an incline of angle theta 37 with respect to the horizontal. Assume that there are no friction between the object and the incline and between the pulley and its axis. At the beginning, the spring is in its relaxed state and the cord is just taut. The mass is at rest. Find the velocity of the object after it slides down delta L equals 1.0 meter along the incline from rest. Study from rest. We look at this, we try to solve it from the Newton's second law, both for translation and rotation. We look at this one. This is a spring is going up, X, and it has a force, P2. And what the P2 equal to Kx in magnitude. And then we look at this disc, how many forces acting on it? This free force from the spring, this tension from the core. And we also have a force acting on its axis, the gravitational force and some other forces. Let's look at the axis, okay, the torque. Gravitational force in this end does not have torque around this axis because r is 0. So we write this equation for rotation. We have TR minus P2R equals I alpha. This I is given. Alpha is the angular acceleration. Then we see the block M. It has 3 forces: mg, tension T, and normal force. It is moved around this direction. When it's going to move up, the M move down. So we have mg sine 37 degree minus T equal to M8. Now we have a 3 equation. Okay. How many unknown? The pitot, x, t, alpha, a, altogether the 5. So we need 2 more equations to solve that. First, when you see the a and alpha, okay, what is the a? A is this one, a. Actually, this is a. So we look at this a as relationship with its angular acceleration is a equal to r alpha. And one more is this acceleration is related to x, okay? A equal to second derivative of x. Wow. So from these 5 equations, principally we can find the answer. What we do, now we look at, we put the k, P2 insert this one, okay? So we get T minus kx equal to I alpha over r. We move this r over here, okay? And we also have r alpha equal to a over r. So a over r, you get this one, right? Then we put this t equal to kx plus this one in this equation. So we get mg sine theta minus kx plus I a r squared equal to m8. Now, seems we can find a? No, we have x, okay? X is related with a. So what we do, we put a equal to this one. So we put a, move this a into positive. So you could I over r squared plus m8. This a is this one, high. It's multiply complicated. So let's continue this one. We write this a as dv dt, okay? And dv, this is x, this is a v. What we want to find, what we given? We given is when it's moved down 1.0 meter, what is its speed? Okay? So what we do, x v, we're trying to get it. We multiply 1. We know this one, we change this to dx dt. So what happened? This is a dv dx. This is a v. So we will move dx over there. We get, this is v, so this is v dv. Oh, because we given x 1 meter, we want to find v. So we have a hope. So what we do the integration. From v equal to v0 at the beginning, and x is to 0. When v equal to v, x equal to L, 1.0 meter. In this case, we can find the answer, okay? We do the integration, very easy one, okay? We find the v. We put m 2.0 kilogram. Spring constant K equal to 20 Newton per Newton. Theta 37 and I is given 0.50. We get R equal to 0.30, L equal to 1.0. We get V equal to 0.69 meter per second. Okay, it's very complicated. don't panic. Is there any easy way? Yes. We do it in different way. Okay. Since there's no friction, so we know the mechanic energy must conserve. What means mechanic energy conserve? That means delta U plus delta K equal to 0. In this case, we have two delta U. One is from spring, one is from gravitational force. So we have delta U gravitational force plus delta U spring plus delta K equal to 0. Now, we try to get 1, 2, 3 different color. Delta G, when it moves from here, starting to down, the potential energy decrease. How many? Because this is air, so this must be air sine theta swing. It's minus. mg air sine theta is mgh. Okay, this is air, this is sine, this is h, right? Look at the spring. The spring originally is 0 and is extend x, so we get delta ux half k x squared. X is finally is air, is 1 meter, this is air, so air squared. And the kinetic energy originally at the beginning is 0. At the final, we have this one, half m squared, and this one half I omega squared. And omega is equal to V over R. All right, then we get it. Then don't forget this term. Okay, you have it. Then put them together. The red one, the black one, the blue one equal to 0. We put this one here, and very easily we get V equal to 0.69 meter. Same answer. See how powerful this conservation kinetic energy. Another sample. A massless rope is tied around an axis of radius r, this is small r, which connect two wheels with the same radius big R, mass m, and inertia I0, mr squared over 2 about their common axis. If the tension of the rope T, assume is this one, find the friction force from the earth. Now let's see. We draw the free body diagram of these devices, okay? How many forces actually? The tension from the rope, friction, the gravitational force mg, and the normal force m. Which direction of the friction? Going forward or going backward? We don't know. You can assume any direction you like. If you do it right, you will get the same answer. Now, in this case, I assume the friction is going backward. Okay. Then let me write down the equation from Newton's law. First thing is T minus F equal to ma com. Rotation, you can see along this one, and we have T small r plus is T small, those is friction, plus F big R equal to I alpha. Okay, and we know these two equations, we have 3 unknown, T, F, T, we have 4 unknown, so it's not enough. We need a relationship. What relationship? We just say A comma, this one. Okay, so this A should be angular velocity alpha big R, right? And then from these 3 equations, okay, the T is known, so FAA, 3 unknown, 3 equations, we get F. Very simple. It's also junior high school math. Then we look at the friction F. If 2R larger than big R, this is positive. So F is positive. What does this mean? F is this direction, as I assume, positive direction. If 2R equal to big R, then F equal to 0. If 2R is smaller than big R, this is a negative number. F is negative. What does it mean? F is negative is the direction. So this is direction. It depends. Sample. Rod CD of length L1 is rigidly and perpendicularly joined with another rod AB of length 2L2 at point C, the middle at point AB. The mass per unit length of both rods is mu, and the system is free to rotate in a vertical plane about point D. If the system is held with AB vertical and release, calculate the angular velocity when AB is horizontal. Okay. Definitely, there's no friction involved, so this is a mechanical energy conserved. Involved rotation. Okay, and the rotation energy is half I omega squared. We need to find the rotational inertia around point D. First, we see what the rotational inertia of AB around D. We use the parallel theorem. First, we'll find its rotational inertia around C, axis around C parallel to D. Okay, this one, we know that one. You can check the table. The AB around C is mL squared. This is from the table. Detail. The M is length 2L2 multiplied by its density, linear density mu. This is M. And this L is 2L2. This is L. So this is the straight answer. Okay, I call it match your seat with the ticket number. Okay, one by one. The red one, the black one. How about AB around inertia around D? We use the parallel axis theorem. This is equal to this one plus the center mass to this one. Okay. This is the inertia. So the center mass inertia. And then we have put the center mass. What is mass? Mass is 2L2 mu. What is the length? Length L1. So we put mR squared. So this is the ABD. And this rod around D is very simple. We know is about mL squared over 3. M in this case is L mu, L1 mu. L means L1 squared. So we get all this information prepared. Okay. Now, then we do it. The total rotational inertia around D of this two rod is put them together. 1, 2. Okay, that's the one. Now, this is just simplify. I'm not going to do it, okay? Now, let's do the physics. When it's going down, we know the mechanical energy conserved. What does this mean? This means delta U plus delta K equals 0. Here is only gravitational force inertia potential involved. What the delta V? Delta V is definitely the potential decrease. It's include two parts. AB part is going down, so the center mass going down is L1. Okay, and this L1, when it rotated, the center mass going down half L1. Okay, with this physics, notice we note it's from two parts. This is minus. This is M2L2 mu, mg at L1 go down. And this one is mu L1 is mass, is half L1. This is delta U. Delta K is easy. It originally is is 0. So delta k is half omega. We just calculate ID. So we put them inside. We get this one plus this one equal to 0. And then we can find omega very easily. Okay. That's it.